Hello and welcome to the show. Today, we're venturing into the incredibly small, fascinating world of quantum mechanics, specifically how scientists are now able to watch individual atoms interact as they float freely in clouds. It's like having a new window into a hidden dance. A key part of this is cooling atoms down to incredibly low temperatures, think near absolute zero. At these extremes, the quantum properties of atoms take center stage. Scientists use techniques like laser cooling in special magnetic traps, followed by evaporative cooling. This lets them create exotic states of matter like Bose-Einstein condensates and Fermi gases, where atoms essentially act in unison. But how do they actually see these tiny interactions? One groundbreaking technique is atom-resolved microscopy. Imagine this. First, atoms are loosely trapped, often using laser beams, giving them space to mingle. Then, suddenly, a light lattice is switched on, freezing the atoms right where they are. Finally, another laser illuminates these trapped atoms, making them fluoresce. The light they emit reveals their precise locations and how they're interacting. This has given us the first direct images of fundamental quantum behaviors, like bosons clustering together and fermions forming pairs, all happening in free space. To get these images as clear as possible, scientists are also developing clever image correction algorithms. Some even use principles similar to facial recognition software, but for atoms, reducing interference and improving the quality of data about the atom clouds. Another powerful tool is quantum gas microscopy, especially for atoms arranged in lattice structures. This helps researchers explore complex models of quantum behavior. For instance, using elements like erbium, with its strong magnetic properties, allows for detailed study of dipole-dipole interactions. So, what amazing quantum behaviors are being observed with these methods? Picture this. Quantum tornadoes, where rapidly spinning quantum fluids of ultracold atoms deform from a round cloud into a thin, needle-like structure. Scientists have also seen Pauli blocking in action. In very dense, cold atom clouds, atoms can effectively become transparent to light. If all nearby low-energy states are occupied, an atom simply can't change its state by scattering a photon. It's a phenomenon predicted decades ago, now seen directly. Then there are edge states, where atoms flow without any resistance along the boundary of an ultracold atomic cloud, a bit like how electrons can move frictionless along the edges of some exotic materials. This could be huge for super-efficient energy and data transmission. And perhaps most excitingly, researchers have successfully achieved quantum entanglement between two separate ultracold atomic clouds, a big step for quantum computing and communication. These techniques also let scientists study various quantum correlations, exploring how many particles are needed to mimic a macroscopic system. And this quest for understanding isn't confined to Earth. NASA's Cold Atom Lab on the International Space Station is also in on the action, studying ultracold atoms in microgravity, which allows for even longer observation times and potentially colder temperatures. In essence, these advancements are providing unprecedented views into the quantum realm of atomic interactions, confirming theories and paving the way for incredible new discoveries and the development of transformative quantum technologies. Thanks for tuning in.